Okay, so we are going to continue our calculus. Let me just review a little bit what we have done in last week. So we have defined intuitively the limit with terms or with the tools limit. It means that we are approaching a function or f of x as x approaching a, and we can say that the function is approaching a finite number. Okay, that's how we usually read the limit. So the functions will be defined when x is near a. And this point means that some open interval having a except not at a itself. So it means that it doesn't need to be an exact point at a. Like for example, this limit here. We have a function. Okay. Let's say we have x equal 1, and this is our functions. Okay. Of course, when we are evaluating the functions at x equal 1, we know that it will be undefined, right? So based on these functions and based on what happened at that point, we know that at f1, there will be some undefined, okay? Well, if we approach using our tools limit, we know that nearby 1, let's say maybe here we have 0.99999, okay, here. And in here, and on the right side, we have maybe 1.0000 something. Okay. So based on that, and based on how close that number. So we learned some functions like the sine pi over x, which is when x approaching 0 is not exist. We learned about infinite limits. Okay. We learned about infinite limits, and remember that the infinite symbol is not a number, it's an abstract, it's an idea. So when we write down infinity, means that it can be add as much as you want. It can be made as large as we please. Okay. So we are not saying that the value is not defined, but we can say it can have some infinite number because we can add as much as we want, and I think it's visually understandable when you have the graph. Okay. When you look at the x as x approaching 0, it has some behavior that it's going up, all the way up, right? Or if you look at the idea of the vertical asymptote, okay, that if one of the following is true, then of course it will be a vertical asymptote. Either you can just approaching only from one side, just right side or left side, you will have the asymptote. Okay, so asymptote doesn't need to be approaching from both sides. If you just have one side, it's still considered as asymptote. Okay, it's like we have this, for example. Okay, from right side and from left side, it has different property, right? One side it goes up, one side it goes down. So it's a positive infinity and negative infinity, but they have the same vertical asymptote x equals 3. Okay. The difference is just how the functions behave. One is going up through here, and one is going down. Now, some suggestions for you. If you have probably given some functions like this, let me just write here.
2x, x minus 3. Okay. If you want to know or to make sure which one is going up, which one is going down, you can try to look on if we add some value or if we replace x with some numbers. Okay. So replace some numbers with maybe 3.1. If this is minus 3, it's just 0.1, right? It's still positive. So the right side of 3 will going up, okay? If we look from the left side, let's say we have 2.9, it will be negative, right? It will be a negative. That's why it's going down, okay? So whenever you find any function, fractions, and you want to know whether the limit is going to be having a positive infinity or negative infinity, you can try some axes. Okay? You can try some numbers, you can try some, of course the easy way to try the numbers is to try so that the difference of those numbers is small enough. If you try maybe 4 or maybe 5, I think this number not an ideal number to check the limit, okay? Because sometimes it may be different, really different value. Okay? Okay, but I think this is easy functions to look at. But sometimes the functions can be more complicated, but still, you still can see how the signs will changing. Okay? It's a suggestion if you like to guess whether it's going up or going down. Okay. Okay, let me continue a little bit. This, okay. Okay, I think this one. Okay, another functions that has vertical asymptote that is quietly common. You can find in many conditions, because it's a trigonometric, it's a tangent. Okay? So tangent, if you look on how the curve, okay, it has the vertical asymptote, and at one, if you will look on the middle one here, they are going to have positive infinity and negative infinity. Okay, and it's repeat, or it's the cycle will be above pi over 2. So every pi over 2, it will have the vertical asymptote. I think it's quite common. I hope you're still familiar with this. And also the vertical asymptote in ln, okay, in logarithmic scale. If you look here, we'll look at that this is going to have a negative infinity, right? Going down. Okay? So when we have limit as x approaching 0 from the right, let's just say that, of ln x, this will result negative infinity. Okay, let's just review a little bit on an infinite limit. Okay. 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 Okay, let me, if this, okay. This is just a review, property of limit. There's another property. Let me just write 5. That is a limit as x approaching a. We have a power n. Okay. We can write this as limit and we can write n as a positive integer. And the other property is the root. But I think root and power, it doesn't really that different. So it's, you can write as a one subject. Okay, if n is even, we assume so the assumption seems to be greater than 0. Okay, now another special case is we have limit as x approaching a of c is also c. Okay, it's just a constant. And when you have the limit as x approaching a of x, okay, we can actually write down as a. This is quite easy to understand because we have some intuitive definition of limit, right? We have intuitive point of view that when we approach the limit or when we approach some functions, of course we approach according to the x-axis, how much x is close to a. But then we haven't really have exact definition of limit. We have intuitive definitions from what we have done, but we haven't yet done some proofs on how close it is. Because we always say that, oh, x approaching a is closer, so that the function is closer to some L value, but we haven't, or we are not sure how close, right? So in mathematics, we need to have some definitions, although if you learn or if you study the precise definition of limit, it seems the definitions itself it's kind of forward and backward, and then we need to reverse the equations, but that is in mathematics. So we need to have the exact solutions, the exact proof, like how small, if it is small, how small it is. But later we will have that. But before that, let me just continue with this one. So the other property is if we have some power n, x with power of n, and because of the previous property, we can write this as a power of n, and n is as a positive integer. Also, we can have the root and as positive integer if n is even, then assumptions that a is positive. Of course, a need to be positive. Now from this all property, we comes up with some method to evaluate the limit, okay, with this property. The first one is direct substitutions. Let me just write the theorem. If f is a polynomial or a rational functions and a is the domain of f, then example. Let's say we have this simple example first. If we want to have step by step how this can be solved, okay. If you remember the property of the limit, then this will turns out let me just show you slowly, and then later we will get when we have already established our idea, and I will skip some processes. Actually, this is what is happening when we evaluate through limit. Of course, if you're already familiar and already used to, we can just plug in this still the same. But actually, the process is all this will be limited by the closed limit as x approaching 5. And we can write this 2 going out like this, okay? And then we can write down, because of the direct substitution, we can write down that this is, or in our case, this is the same as if f of x is 2x squared minus 3x plus 4, then If we plug in 5, this will be the same thing as 39. Okay. It's still a simple solutions, a simple functions. However, the case on the second limit here, the fractions, when we try to plug in 1, this will result 0 over 0. Now we call this actually indeterminate form. But we will learn indeterminate form later on around chapter 6. But for now, when we have this, so when we have this, there are several methods that we can do. Okay. The first method is if you can try to factorize. Is it factorizable? Factorizable. Then you can factorize first, or you simply put, you can manipulate the algebra. So let f of x is, okay, and we can simply write down or factorize this x squared minus 1, and we have x minus 1. So we may have the x plus 1, okay? Okay. So can we write that x squared minus 1, 5x minus 1, if this is f of x, can we write this x plus 1? Agree? Who agree with me? Okay. If you have some free time, you can check in your graph. When you draw the graph in a graphing calculator, of course, these two will go by line equation. But if you check at x equal 1, if you zoom into this one, you will see some. Let me just show you. Okay. X squared x minus 1 minus 1. Nothing wrong with that. X plus 1. Okay. Okay. Let me just hide the x plus 1. Okay. Seems same, right? Seems same, but like I told you, where is x equal 1? Oh, here. So let me just go. See it? It's the same as x plus 1. It has some hole. Okay? So what we are dealing here, okay?
not the same. Okay? Very simple. But if you just say that this is just an equation and you want to simply cancel out in this process, you can do that. But if you think this in terms of functions, this is two different functions. Let's just write. This is f of x, and this is probably g of x. Although they have the same line, but they are different functions. Okay. But this is when we are talking about functions. But when we are talking about limit, we already established our definitions, right? About limit. If we have a whole, the limit is just as it is, right? So we can say the limit, this is actually the same. Okay? So that's how the process, okay? How you understand the limit. Okay? So if you think in the terms of functions, they are different functions. But in terms of limit, when we evaluate as x approaching 1, they have the same finite value L. Or in our case, this will be the same as 2. Okay? And that's why when you have like calculations, maybe since you're high school, well, what will you do here? Oh, we can factorize, blah, 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 and then we have 2. But actually, it's more than that. It's more than that. Okay. So we can, maybe we can write some theorem. So if f of x equal g of x when x is not equal a, then limit as x approaching a. This is what we have done on the example, and we need to provide it. We need to provide the limit exists. Another example that you might find is if you have a piecewise definitions like this one. Of course, x plus 1 you can draw line y equal x and then move up 1 unit. So let's say as x equal 1 here, so we will have some hole. Maybe I will draw the hole like that. Okay. And then at x equal 1, it's going to be pi. Pi maybe around here. Oh. Okay, so pi around there. Let's say this is pi.
This is x plus 1. So the limit as x approaching 1, let's say from of functions gx, okay, it's still, we look on this x plus 1. Okay? We look on this x plus 1 because we, in terms of limit, then this is the same as x plus 1, which is 2. Although the g equal 1 is pi. So g equal 1 and the limit is different. Okay, so we provide the limit exists. But, okay, here we are going to have some connection with next sections, which are the continuity. Okay. But because this is not the same result, we call that this is a discontinued function. Okay, so we call this is discontinued, or discontinuity happen. Another way that what method that you can apply, okay, aside from what we have later on the L'Hopital rule and others. Let's say we have limit as x approaching 0. Maybe I will just turn this off. It's kind of I said as limit x approaching 0 okay. Of course, when we look at this limit, when we try to put our 0, this will be resulting of 0 over 0. Again, it's our indeterminate form. Okay, and before we conclude with the L'Hopital rule, we may have several methods to try. This is called the rationalizing. Okay, the way we are going to do it is we are going to multiply this limit, or the numerator of the limit, with its, like if it has a minus b, then we need to multiply with the a plus b. Why? Because in algebra, if you remember, because of this property here, we may need to have a squared and b squared. Okay? If we multiply with the same signs, it doesn't seem to be simplified, right? Because it has a new terms here. We want the terms as simple as possible, and so the way we are doing it is we need to have the opposite signs. Okay, that's why. Okay. Okay, so we can have this, and we try to calculate x squared plus 9 minus 9. And just my suggestions, whenever you see any big chunks, calculations, multiplications, just write down first, okay? Do not attempt to try multiply one by one, exactly. Unless you are having this already simplified, okay, I can take this a plus b, a minus b, and I can go to the a squared minus b squared, okay, because it will be simplified. So the numerator, we can do it, and the denominator, just leave as it is. Okay. Now, one by one, we can see it's canceling, and we have now x squared and x squared canceling. Okay. Now we can try to evaluate, substitute 0 to x, and we see that it's going to be 3, right? 3 plus 3 is 6, so 1 over 6. Okay. So rationalizing. Okay, the other thing is we can use or using the one-side limits. Let me just write this theorem. I think I already write before. Let me just remind you this two one side is limit. This is L, and L also equal with the right hand limit. Okay, for example, we can look on this, the absolute value of x. Okay, we can write the absolute value of x as a piecewise defined functions that is composed on x and minus x, right? This if, of course, x is positive, and this is if x is negative. So we can have two approaches. Okay, first from right side. This is for x positive. For x negative, we can have approaching from the left. it seems it's going to have the same value of 0. And then by the theorem, because of the right hand and left hand, it's the same 0, then we can say as a conclusions that limit let me write completely or you can just write directly the answer. It's fine because you already show that the right hand limit and left hand limit is the same. And I think we can also draw this in terms of okay. Okay, I think we can have some break. Okay, we can have some break. All right. So this is absolute value of x. Okay, let's try another functions. Let's say if I have limit as x approaching 0 of absolute value of x, but with divided by x. Okay, now we have absolute value of x, and we already defined as in previous slide. But we have another denominator that is x. Okay. So of course, because of x at the bottom, it can have a positive or negative value, right? Okay, the total. So first is we can imagine that the absolute value of x, it can be x and negative x, right? This is when x is positive and x is negative. Okay. Actually, to write down which one is having the equal value, you can write in the positive or in the negative. The results still, or the conclusion is still the same, but usually write on the positive one. But then, when we evaluate as x approaching 0 from the right, okay, of absolute value of x divided by x. This is a positive x and an x, right? Nothing wrong with it. And this will result 1. When we have limit from the left, this becomes a negative, right? Now, of course, this will result a negative 1. And since it's different, the limit doesn't exist. And when we try to draw, this is the visuals, the graph. At as x approaching 0, it has two different value, positive 1 and negative 1. Okay, okay, so we say that this limit is not exist. Another function that I want you to observe is let me just write these functions. This means we say this as the greatest integer functions. So we only consider the integer value. So if we apply or input some numbers, okay, let's say from any real numbers, okay, let's say x is any real numbers. If we put 4, it's already integer, so it's still 4. But if you put maybe 4.2, the result is 4. Okay. If we input maybe pi is 3 point something, but it's the integer value is just 3, right? If we input negative 1/2, this is -1. So if we draw that's our functions will be. And then from what we saw here, it seems that at some point there will be the limit doesn't exist. Because it's always have the, especially on the integer value, it's always having a different value, right? Different value. But in between, you can see it still has a line, right? So in between of this interval, we can separate the interval. We see the limit exists, but it seems that at this interval here, there is no limit. Okay? The limit does not exist, and we know that the function itself is it's not continuous functions. Okay. Okay. Let me go through another slide, and let me put the okay, maybe this. Okay. Now we move on to some theorem that is quite helpful to evaluate the limit. It's called the squeeze theorem. Okay, first we approach the theorem. First, let's see the functions f and g. Okay? So if we look on the functions, the f of x is less equal than g. when x is near a, except possibly at a, and limits of f and g, let's say exists as x approaching a, then we can say that this is our idea. Okay, the first idea. Okay, now if we look all three functions, and we know that the f less equal g and less equal of h. Okay, if we look at this function here, okay, let's say near a is maybe here. Okay, it should be like a bit closer, but just to observe, let's just write like this. Okay, so f less equal g less equal h. When x is near a, so that the limit if the limit is equal with some value, then we are sure that the limit on the middle one, the middle functions, is also has the same value L. So the requirements of this is that the g need to be between f and h. Okay, and it can be any function that you know. So if you can prove that g is in between f and h, and you can evaluate the limit of f and limit of h, that is some value. So at the conclusions, you can finally say that the limit on the middle functions will be also equal value. Example of this is you have x squared sine 1 over x. Yes.
Go up to the graph.
Which this graph?
Yeah.
Okay.
Can you zoom out a bit? Zoom.
Maybe here?
Yeah, thank you.
Okay. Now, the example here, okay, let me show you the graphs. Okay, let me show you the graphs. Okay, let me delete this, delete. Let's just input the x squared and then input the function sine 1 over x. Okay, so small. Okay, it doesn't really clearly see, maybe around here. And let me put inside, and then the other one is negative x squared. It's better now. We just look here. Okay, if you just look this functions here, seems that this is not really clear. Or maybe let me just compare with the sine 1 over x, and let me just compare this two. Sine 1 over x. Okay. Okay. Now if you look this green curvy here, the green curve, of course, at the 0 here, it has like fluctuated all the time. And we are not sure whether it's 1 or negative 1, right? Okay, then compare with the x squared sine 1 over x. It's much more diverged, right? It's much more, not diverged, converged into one point here, right? Which is 0, right? And if we look here and we, let's say, because we have x squared, right? Let's just compare with this x squared and minus x squared. Okay? And let's just see how it looks like. It's perfectly aligned, right? Perfectly aligned. Why is that? Because our sine will always have maximum value 1 and minimum value negative 1. So you can think this x squared as the top functions. The middle one is our question, and the lower function is this negative x squared. And that's why we can use the squeeze theorem. Okay? If we look on the graph, I think the graph can be much more clear, right? To understand how the squeeze theorems work. So from there, we are going to have, first, the sine itself is having this value, right? So if we multiply with negative, or we multiply with x squared, it will be this. And then we take the limit of each of them. Then this happens. And we know that the limit, the negative x squared, it's 0, right? The x squared is also 0. Then the conclusions will be that this limit by squeeze theorem limit is 0. Okay. That's how squeeze theorem works. Okay. Now the next section is I will go through the precise definition of limit. Okay. So precise definition of limit. So let's say we have a piecewise functions. Okay, intuitively, when we draw the graph and then look on the numbers and we consider the limit, okay, if we take the limit as x approaching 3 of our functions, that will be resulting 5, right? So when x is close to 3, f of x is close to 5. That's how we understand the limit, okay? But the question is, like I said before, how close to 3 does x have to be? So f of x difference is 5 by maybe less than 0.1. The 0.1 is just a number that we consider quite small, okay, to make it easy to understand. Okay, so I pick some numbers here. It can be any numbers that is small, but just to note that we need to know how close the limit is. Okay. Okay. If the distance from x to 3 is, we write in terms of distance terms with absolute value, and distance from f of x to 5 is f of x minus 5. So our problem is the difference on the functions will be less than 0.1. That's our problem. Okay, we state 0.1 at the beginning, so we write that we want to take the closeness of f and the number of 5 to be less than 0.1. That's our statement problem. Okay, and then we want to know how close x to 3. That's the one that we want to find. Okay. So this will be if the distance is less than delta. So the delta is the distance that we want to observe. Okay. This is also x is not equal 3, right? From our statement from the piecewise definitions. Okay. If the distance is a positive value, then x is not equal to 3. So we can also write this is in between 0 and delta. So we ensure that the delta is a positive value as well. And then from this value here, if 0 let's say we try to divide 0.1 divided by 2. Like we suggest a number. So here is suggesting some value for delta. Then the distance is in between 0.05. Okay. Then we turn back to our f of x. Okay. So then if we put our functions to x minus 1 with piecewise definitions, then we will have this will be to x minus 6, which is intuitively we can see that this is 2 multiplied by x minus 3. And we know that the x minus 3 is less than 0.05 from our statement here. Okay. So we can write this is less than 2.005, or this is going back to 0.1. And that is this is less 0.1 if 0 x minus 3 less 0.05. So the number delta 0.05 suggests that that is the number that when we use that number, the closeness in functions n5 will be less than 0.1. Okay. So delta will be 0.05, so that this is less than 0.1. Okay, so what we are doing here is we just play with the numbers, okay? But without we realizing, we are actually trying to prove how close the distance from our limit and the value that we are assuming. Okay. So the problem statement is actually this blue color here. Okay. We want to know how close x to 3 so that the distance from the functions to number 5 is 0.1. 0.1 is the statement problem. It can be any number. Okay. It can be any number. So the first thing we did is we try to figure some relations. Okay. Of course, if you look in the problem statement here, or the piecewise defined functions, you know that it's having to x minus 1 with the functions. Okay. And what we did is we put on the value, and then we take some time to see the relations. Okay. And what we are going to find is we are going to try some value of delta so that the difference is 0.1. Okay. Now, in general, this difference for the functions we call also, this is an epsilon. So I have the picture. Oh, not this one. Oh, I haven't checked. Okay, let me go to the next slide and give you some rough picture here. Okay, let's say that's the functions. And the number is this should be 2x minus 1. Or let me just go through the graph here. Let me put here. Okay, maybe here. Okay, I think better just using the graph directly. Okay. Let's say this is 3. Okay. And then at this point, it's having a hole. Okay. And then it's having some number there, 6. Where is 6? Oh, 6 is here. Okay. And 5 is here. Okay. So what we are doing is really we are having some. Let's say we have some value here. Okay. Nearby 3. That is 3 plus delta and 3 minus delta. So this will be delta. And the other value is around 5, which we have the, let's say this is an epsilon, and this is also an epsilon. 5 minus epsilon, so the distance is epsilon. And it will correspond then with the functions. And it will correspond then with the delta. Okay. So we can write the distance is just an epsilon if the distance in between this 0 and some delta, and we say that it's always been epsilon divided by 2. So this is a precise way to say that f of x is close to 5 when x is close to 3. That we can make values of f of x within an arbitrary distance, or maybe within a distance of, okay, maybe just within a distance epsilon from 5 by restricting or limiting values of x to be within a distance of epsilon equal delta epsilon over 2, sorry. It's delta epsilon over 2. And we can write these terms as follow. So 3 minus delta less x less 3 plus delta. This is x is not equal to 3. And then we can write 5 minus epsilon is less than f of x, less than 5 plus epsilon. Okay, so generally, if we write in exact words, maybe I will finish this. I think this is the most important one. Okay, so precise definitions. So let f be a function defined on some open interval that contain the number a except possibly at a itself, then limit of f of x as x approaches a is L, and we write if, for every number epsilon that is positive, there is delta that is positive such that if then okay, I hope you guys understand on this precise definition. So what this means is, what we are going to do is, we are going to evaluate, or we are going to, in real cases, in real studies, when you have a function and you know that the functions can be manipulated in some ways, you know how to relate with the domain, the axis. And we know that there is some epsilon here. The idea is we want to find the delta such that when we have those delta, we are going to have this statement. And when we have those delta, then we prove that, okay, the limit is proven by this precise definition of limit. So it's kind of forward, backward situation in terms of calculations. Okay? So we start from here, and then we assume some delta to have some relation with this epsilon, and we put back into our equation, and then we substitute epsilon with the delta, and we prove that it will going back to the first statement. In the first statement. Okay, maybe giving you one example on how we approach these precise definitions. Okay. Okay, so prove that limit as x approaching 3 of 4x minus 5 is 7. Of course, if we know the limit already, we have the intuitive definition of limit. If we just directly substitute, we know that it's 7, right? We know it's 7. But in precise definition, we need to find the relations, the distance x to 3, and the distance for x minus 5 equals 7. We need to relate the distance. Okay? What's the correlation? And we need to try some value, some delta, so that this is true. Okay? So the first thing we need to write the statement. Okay? The statement first is that the distance here is delta, okay, for x, and the distance within the functions is it's epsilon. Okay, and then consider that if you have these conditions, we can write this as 4x minus 12, right? And we know that this is 4 times of the distance, x minus 3, okay? So we assume, or we want delta such that we can write 4 x minus 3 less epsilon. So we try, okay, so first we try delta equal epsilon over 4, or we choose delta is epsilon over 4, and then the later part we need to prove, given epsilon is positive and delta is epsilon over 4 based on our correlations, then we put back into our original equations, that is this. So this will be resulted in 4 and epsilon over 4. And seemingly, it's going to have the epsilon. So thus, it's proven that it's going to have the same epsilon as we mentioned at the beginning. So thus, finally, if the distance, then therefore by definition of limit, then we have limit okay, of course, the functions is simple enough to see what's the correlations between the distance here and the difference in the function. Okay, any questions so far? Any questions? If not, then at the last 6-7 minutes, I would like to have some feedback from you. If you need to write this, I will give you some time to check the notes. Okay. But I will review a little bit next Friday on how this precise definitions can be solved. Okay. At least usually in precise definition, the proving part is usually the function will not be really complicated. It's not as complicated as the other sections, because this is basically the important point is the essential step that you have to do. It is not exactly to find the numbers, but it needs to be finding the precise way. Okay? Like you need to assume, or you need to choose some delta, and you check the delta, you prove that the delta that's correct, and it's going back to the original functions or original statement, and that is the proof. Okay. So the important part is the structure of the structure, not finding the numbers itself. Okay. At least finding the relation between delta and epsilon. This is the key part here. Okay, if you are ready, I would like to go to the Mentimeter. Okay. Go to the, using the QR code, or just go to the menti.com, is the code. Okay. Okay. Yeah. Or if it is difficult, go to this code menti.com. Okay, if you are entering this. Okay, later you need to, so that I know, okay, you use your ID or maybe name, but I think ID is more clear. There will be some time limit for each question, so maybe 30 seconds to 40 seconds. It's just a simple question, so I hope you don't mind. Okay. I have 4 simple questions. Okay, let's start the first one. Oh, sorry. Okay. I hope it's simple enough. I give you, this is quite long time for this one. 1 minute. I think it should be enough time. You're just checking how you deal with this kind of question. Okay, around 30 seconds, I think. Already 6 students. Oh, 3, 2, 1. Okay. Okay. Okay, most of you did a good job. Okay, who 24? Okay. Okay. Okay, let's go to the next one. Get ready. Question 2. Okay, let's get ready. Okay, this is true or false. Okay, so it should be simple. Okay, good. Okay, 22. Full 22. Okay. Okay, so you go up. Okay, get ready. The other one. Okay. Okay. Okay, so if you still remember. Okay, it's true. One more. And then we will finish. Okay, still same. Okay, last question. Okay, is it true or false? Okay. Maybe you need to look on your phone to get a bigger or clearer picture. It should be false. Should be false. Because remember, both functions need to be exist first. Each function needs to be exist first. And it's 0 over 0, right? 0 over 0 situation. It's the denominator is 0, so it should not be happen. Okay. And that is for today. Thank you for joining.